Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. In today's lesson, we're going to look at the second half of concentration calculations, which we were unable to do in our first lesson. So as a review, we did mass percent, mass volume percent, and volume percent. Today we're going to look at two more, parts per million and molar concentration. Now, molar concentration is by far the most used concentration in chemistry. But before we get to that, we're going to do parts per million. So parts per million is quite useful when you're dealing with environmental chemistry, drugs or pharmaceutical chemistry, and body chemistry. So for example, in environmental chemistry, you might be looking at pollution in lakes, but in very, very minor amounts. So heavy metals in lakes or mercury in lakes, something like that, or even mercury poisoning or heavy metal poisoning in the human body. With drugs, a lot of the active ingredients in drugs that we consume, whether it's legal or illegal, are in parts per million. It takes very little for those chemicals to affect the body in dramatic ways. So for instance, it's a very, very small parts per million amount of fentanyl that would kill a human being. Same thing with mercury poisoning. So we're going to look at parts per million here now. And the example I'm going to give to you to kind of give it a concept or a construct that you can maybe grasp a bit better is the concentration of CO2 in air. Now, I know the amount of carbon dioxide in air is talked about a lot because it has a massive impact on our environment, but it's less than 1% of our air, and it works out to about approximately 30 parts per million. Now, what that means in simple terms is if I had 1 million grams of air, 30 grams of that would be carbon dioxide. That's pretty simple. 30 parts of 1 million or 30 grams of 1 million. So here's the equation, which looks very similar to the mass percent equation in terms of the center part of it. It's the mass of the solute over the mass of the solution. The only difference is that a mass percent is times 100%, whereas this is times 10 to the power of 6, which essentially is 1 million. So in a shorthand, I would write it like this: ppm is equal to mass subscript solute over mass of solution. Remember, the solution is both the solute and the solvent. And then we're multiplying that by 10 to the power of 6, and the unit is parts per million. Again, this 10 to the power of 6 is 1 million. The difference between mass percent in this, again, is in this one I'm multiplying by 1 million, and in a mass percent I'm multiplying by 100. Now I have something else here for you that I would love for you to memorize, which is common units for parts per million. So a lot of the time, if we don't use these shortcuts, what you have to do is you have to convert both units to the same mass unit before multiplying by 1 million. So let's say I have something in milligrams and something in grams, and I have to convert both of them into one mass unit, and then I can divide and multiply by 1 million. But if you have a difference in units by 1 million, you do not have to do a conversion. This makes your life much, much easier when you're making a calculation. So for instance, 1 gram over 1 million grams, which would be in the exact same unit, so that's 1 part per million, would be the same as 1 milligram in 1 kilogram. Now the difference between milli and killi in our conversion scale is 1 million. So I don't have to then multiply by 1 million if I divide milligrams by kilograms, because the difference in their unit is 1 million. So the question we're going to do, I'm going to do it both ways. I'm going to convert to 1 unit, and then I'm going to show you how to use the shortcut. So that would be generally when we're dealing with solids. In solutions, you can use the following. 1 parts per million is equal to 1 milligram per 1 liter of water. You guys know that 1 kilogram of water is 1 liter of water. That's how the milliliter unit was constructed. Okay, so let's look at this first question. It says mercury poisoning symptoms begin when 20 milligrams of mercury has accumulated in an adult human. Calculate this concentration as parts per million for a 55 kilogram person. Okay, I'm going to do it the long way first, showing that we have to convert units to the same unit. So I have 2 different mass units. I got the mass of the mercury as being 20 milligrams, and I got the mass of the person as 55 kilograms. In order to use the equation the way it's set up, I have to have both the same units of mass. What I'm going to do is I'm just going to convert both of these into grams, which is kind of the middle place to go. So in order to do that for the milligrams, I know that there is 1,000 milligrams in every 1 gram. And so essentially I'm dividing by 1,000. So 20 divided by 1,000 would be 0.02 grams. And then with the 55 kilograms, I would have to say I have 1,000 grams for every 1 kilogram, and I'm converting that unit. So kilograms cancels with kilograms. Up here, milligrams canceled with milligrams. And so I go 55 times 1,000. And so that's 55,000 grams. Now that I'm in the same unit, I can plug these into an equation. So I can go parts per million is equal to the mass of the solute over the mass of the solution, which would be the human, times 10 to the power of 6 ppm. Okay, so putting those numbers in, you'd have 0.02 grams all over 55,000 grams times 10 to the power of 6 ppm. Okay, and I get, as a parts per million, it's 0.36 parts per million. Okay, so that's the long way. I personally wouldn't do it that way, but it is an option. The other way of doing it is get your solute in milligrams. In this question, it is already in milligrams. Get your solution in kilograms. In this question, it already is in kilograms. So a part per million is equal to milligrams divided by kilograms. So all I have to do is take those 2 numbers, 20 milligrams, divide that by 55 kilograms, and sure enough, I still get 0.36 parts per million, but it is a lot easier to work with that than it was to convert both of those masses and then put it into the equation. So again, there's no need to do times 10 to the power of anything as long as the solute is in milligrams and the solution is in kilograms. So question B here, we're still using the same stuff. It just says calculate this by as a percent by mass for the same person. And so the reason we're doing this question is to show how similar the 2 equations are. I've already converted both of these units into grams, so that's done for us. I'm going to bring those numbers down. And the only difference in the equation is I'm going to multiply by 100 rather than multiplying by a million. So mass percent is the mass of the solute divided by the mass of the solution multiplied by 100%. Again, this is mass percent, not parts per million. I'm going to take my masses from above down, so I have to have the same unit, 0.02 grams, all over 55,000 grams. Multiply that by 100%. So, And so this would come out to 3.6 times 10 to the power of negative 5%. So what I would like you to do at this point is to read the following question, which talks about DDT and requires you to figure out the solute concentration of DDT in a trout and see if you can solve the problem. So pause the video now and then come back when you're done. Now that you've had the opportunity to try the question, we're going to take out the important parts from this question. So the first thing we notice is that the parts per million of DDT was 16, and that the mass of our trout was 2.5 kilograms, and that this was the solution. Just like in the previous question, the human being was the solution. In this one, it is the animal, it's the fish, that is 2.5 kilograms. Now there's two ways of us doing this. We can use the full equation that goes times 10 to the power of 6, and we'll get the mass of the DDT in the trout in kilograms, or we can use the shortened version and we'll get the mass of DDT in the trout in milligrams. And I prefer the shortcut. So again, what the shortcut is the fact that a part per million is equivalent to a milligram per kilogram of solution, because the difference in the milli to killi conversion is 1 million. So I'm going to substitute my numbers in. I have 16 parts per million is equal to an unknown mass in milligrams of DDT all over 2.5 kilograms of trout. In order to rearrange this, I have to do the opposite operation of division, which is multiplication. So I'm going to multiply 2.5 kilograms up on both sides. That's going to cancel that out. And so this is going to give us a total of 40 milligrams of DDT in a trout if the concentration is 16 parts per million. The next type of concentration we're going to look at is by far the most important in chemistry. It's called molar concentration, or sometimes called molarity. And it has two units. The fundamental unit itself is the number of moles of solute divided per liter, or in a shorthand, it's capital M. Now this can be confusing because capital M is used as a variable for molar mass, but this isn't a variable, this is a unit. Now, all of our calculations, we're going to do moles per liter. However, if you're in a lab, the bottles will be labeled capital M, as in like 1.0 molar hydrochloric acid. It's just shorter, so it fits better on a bottle. But again, the fundamental unit is moles per liter. Capital N, molarity, is moles per liter. It's just a shorthand, okay? So the equation is the following. Concentration is the number of moles per volume. Capital C stands for concentration. Okay, this is in moles per liter or molarity, either or. The N stands for moles in the unit of the mole. And really, really importantly, the volume, capital V, this is volume, it must be in liters. This is in liters. Do not forget, there is 1,000 milliliters in every 1 liter. Now there is a variation of this. A lot of the times we're not given the number of moles, but rather the mass, because when you're in a lab, we don't have a thing called a mole scale. We only have a mass scale. So a variation of this is C is equal to little m over big MV, which essentially combines C is equal to N over V with N is equal to M over capital M. Now, little m on top stands for mass in grams, and capital M stands for molar mass in grams per mole. Now, we know that molar mass is calculated using the atomic masses on our periodic table, and I'll do a quick review for maybe one or two of the questions, but it is previous knowledge. So what we're going to do is a series of equations, and we're going to start with easy ones, and we're just going to gradually build up the difficulty. All right, so the first thing, 0.5 moles of sodium chloride is dissolved in 0.30 liters. So the first thing I notice is my unit is already in a mole. It's not in mass, so I don't have to do any conversion there. And I also notice that the volume is in liters, so I don't have to do a conversion there either. So this is 0.5 moles and 0.3 liters. I would simply go C is equal to N over V. I would substitute in those values, 0.50 moles all over 0.30 liters. And easy peasy, we get 1.7 with rounding moles per liter. Okay, so what you can do as we continue through here is you can pause the video between questions and give them a try before I go through the answer. I will just briefly pause between the questions to give you that opportunity. So if you wanted to try B on your own, pause the video now. And if not, we'll continue on. Okay, so for B, it's talking about iron 3 chloride, and they have given us the number of moles. So I have 0.289 moles of iron 3 chloride, and it's dissolved in 120 milliliters of solution. Now the milliliters immediately jump out at me. This is the incorrect unit for the use of C is equal to N over V. I need to convert this into liters. So my volume is 120 milliliters, but I have to convert that to liters. In order to do that, I would divide by 1,000. So this would be 0.120 liters. I can then now substitute into my equation C is equal to N over V. So I've got 0.289 moles for every 0.120 liters. I plug that into my calculator. And I get a total of 2.408, which would round to 2.41 moles per liter. Okay, question C. If you want to try it on your own, pause the video now. If you don't, we'll solve it together. Okay, so we have something different here. It says 5 grams of calcium chloride. So I don't have the moles. What I have is mass. It's 5.0 grams of calcium chloride. I have to figure out the molar mass of calcium chloride first. In order to do this, I have to look up the ion charges on calcium and chloride. So this is Ca2 plus and Cl minus. And I've got to write out the equation for calcium chloride. So this is CaCl2. Now, in order to figure out the molar mass of calcium chloride, I have to look up their masses on the periodic table. So for instance, calcium, group 2 metal, has a mass of 40.08 grams per mole, and chloride has a mass of 35.45 grams per mole, but I've got 2 of them. So what I got to do is I got to add the mass of calcium to the mass of 2 chlorides, which gives me a total molar mass of 110.98 grams per mole. So I'm going to put that over here, 110.98 grams per mole. I also have a volume, but it's not in liters. So my volume is 50 milliliters. I have to convert that by dividing by 1,000. So 50 divided by 1,000, and we have 0.05 liters. So I've recognized that I have mass, not moles. So I'm going to have to use the equation that has mass in it. So C is equal to mass over molar mass volume. So the mass is going to be 5.0 grams divided by 110.98 grams per mole. And that's multiplied by our volume, 0.05 liters. We'll put that in our calculator, making sure that we double bracket the denominator to make sure it follows bed mass. And we get a concentration of 0.90 moles per liter. The units would cancel, so grams on top, grams on the bottom. And so we're going to get moles over liters. Perfect. Okay, let's try the next one. If you want to try this question on your own, you can pause the video. Just remember that salt, we're going to assume, is sodium chloride when we're doing the question. If you still need help, continue to watch, and here we go answering the problem. All right, first thing, we have a volume of 250 milliliters, which we have to immediately convert to liters. So divide that by 1,000 and you get 0.250 liters. Now, the next thing we're given is a concentration. Okay, so the concentration of this solution is 0.56 moles per liter. And we're actually being asked to calculate the mass of the salt. So the mass of NaCl is equal to question mark. And because I have mass, I know I need molar mass of salt. So I go to my data book, I look up sodium. The molar mass of sodium is 22.99 grams per mole. And I only have one of them, so 1 times 22.99. And then I have one chloride, so 1 times 35.45. And so the total molar mass for this compound is going to be 58.44 grams per mole. Now I have all of the information I need to make my calculation. We're just going to have to rearrange our equation. So we have C is equal to M all over MV. I need to isolate mass. So in order to isolate mass, I'm going to have to multiply molar mass volume up to the other side as such. That's going to cancel those out. And what I'm left with is mass is equal to CMV. So let's put those numbers in there. The concentration is 0.56 moles per liter. The molar mass is 58.44 grams per mole. And the volume is 0.250 liters. We're going to cancel out the liters. We're going to cancel out the moles. And we're going to put this into our equation. And so your total mass here would end up being 8.2 with rounding grams. Now I do want to show an alternate method for answering any of these questions, but especially question D, which is using unit analysis or fractions, which is generally what we're going to do when we get to solution stoichiometry. But it's also what a university professor would do. They really wouldn't be using equations so much, like C is equal to M over MV. Okay, so unit analysis simply uses fractions to cancel out units until you get a unit that you want. So for instance, once I know I need to have molar mass, concentration, volume in the right unit, so all this work in blue is correct and I have it done, what I would tell myself is I would like to start with the unit that has a single, that has the unit that I want to solve for. So for instance, I want to solve for grams, and out of all of these things, I have liters, moles per liter, and grams per mole. Well, grams per mole has a unit of grams, and so what I want to do is put grams on top of a fraction, and this continue to cancel out units until I'm only left with grams. So for instance, I would start with this. I have 58.44 grams for every 1 mole. Because that's what this unit is. It is a fraction. It's grams per 1 mole. Then I'm going to set up my next fraction. And I know I want to get rid of the unit of mole because my ultimate goal is to be left with grams. So I'm going to put moles on the top of the next fraction. Now, where am I going to get this moles from? Well, if we look back up here, concentration has moles in it. So this is 0.56 moles for every 1 liter. So what's happened is the moles on the bottom cancel with the moles on the top. And right now I actually have a unit of grams per liter. So if a question asked you how many grams are in 1 milliliter, this is what I would do, and I would calculate this and get an answer. But the question just wants grams. So I need to get rid of this unit of the liters. I'm going to put it on the top of the next fraction. I'm going to go back to my list and say what has liters in it. Well, volume has liters in it. So I'm going to put that on top in order to try to cancel out that unit. So 0.250 liters, and I get liters canceling out with liters, and I'm only left with the unit of the grams. Now, how I would put this in my calculator is simply everything in the numerator in one set of brackets, so open bracket, 58.44 times 0.56 times 0.25, close bracket, hit divide, open bracket, 1 times 1, close bracket, equals. Now, this will give us 8.2 grams. And if you look and compare what I've done down here with unit analysis with what's up here in red, it's actually the exact same thing. We did 58.48 times 0.56 times 2.25. Down here, we did 58.44 times 0.56 times 0.250. It's just a different way of showing your work. And I don't care which way you choose to do it. Whichever way works best for you is best for us. We're now going to look at the one final twist on molar concentration, which is to calculate the concentration of ions in solution. It really only requires one more step past what we've already learned, and it's not a very difficult one. But we do need to do a dissociation equation in order to figure out the number of moles of ions, because there is a mole-to-mole ratio. So let's look at the first question here. It says calculate the molar concentration of sodium ions if 2.7 grams of sodium carbonate is dissolved in 175 milliliters of water. So let's start with sodium carbonate. That's Na plus, and carbonate is CO3 2 minus. So if we were to combine those, it would be Na2CO3 solid. I'm going to dissociate it into Na plus aqueous and CO3 2 minus aqueous. I'm also going to balance it with coefficients, so there should be a 2, 1, and 1. The next thing I'm going to do is I'm going to write down the information that I know based on the question. So it says calculate the molar concentration of sodium ions if 2.7 grams of sodium carbonate. Now they're not saying the grams of sodium, they're saying the grams of sodium carbonate. So I know the mass here is 2.7 grams. And I also know that it's dissolved in a volume of 175 milliliters, which I will immediately convert to liters, so 0.175 liters. The next thing I realize is I'm going to need a molar mass of sodium carbonate. Because this mass is of sodium carbonate, I need the molar mass of sodium carbonate. So I've got 2 sodiums, 1 carbon, and 3 oxygens. So it would be 2 times sodium's molar mass of 22.99, plus the molar mass of 1 carbon, 12.01, plus the molar mass of 3 oxygens, so 3 times 16. And so that gives me a total molar mass of 105.99 grams per mole. And now it's possible for me to solve for the concentration of sodium carbonate. Now I understand that's not the question. The question is asking for the molar concentration of sodium ions. This is my goal here. I need to know the concentration of this. The only way I'm able to do that, though, is to get the concentration of the information I do know, which is sodium carbonate, and then do a mole-to-mole ratio, basically just multiplying by the coefficient to get the concentration of any of the ions. So, starting with this, it's 2.7 grams of sodium carbonate, all over, double bracket, 105.99 grams per mole. Multiplying that by the volume of 0.175 liters. So I got 2.7. Okay, so this would work out to 0.14. Let's say it's actually 1.5 with rounding, moles per liter. Now, what I would do to get the concentration really of either of the ions, it doesn't really matter, is I need to cancel out the moles of sodium carbonate and make it the moles of that ion. I would simply just multiply it by the coefficient. So this would be multiplied by 2, which would give me 0.30 moles per liter. I'm not sure if the rounding would make it 0.31 or 29, but close enough. And then this one would be the exact same because I'd be multiplying this by 1, so this would be 0.15 moles per liter. So I know the concentration was only about sodium, but in order to get there, we had to do the concentration of the solid dissolved and then multiply the coefficient, which is essentially just doing a mole-to-mole ratio. What I'd like you to do now is read this question and try to do it on your own, starting with a balanced dissociation equation and going from there. Please pause the video now. Okay, now that you've had a chance to try the question, let's go through it. What is the molar concentration of calcium ions, which would be Ca2+, if this many grams of calcium phosphate, Ca2+, phosphate is PO4 3-, is dissolved to make 3.95 liters of solution? So we would start with our solid, so Ca3, PO4, 2 solid. You split that up, you have Ca2 plus aqueous, and you have PO4 3- aqueous. And then we got to balance it, so we're going to need 3 moles of calcium ions, 2 moles of phosphate ions, 1 mole of my solid. Write down all the information we know, so the mass here is 1.3 times 10 to the negative 4 grams. Our volume here is 3.95 liters. No need to convert. I'm going to need to know my molar mass. So make sure that you understand when it comes to the molar mass, we have 3 calciums, 2 phosphoruses, and 8 oxygens, because this 2 is multiplied by the 4, this 2 is multiplied by the 1. We can't forget about it, and of course we have 3 calciums. So let's take a moment to calculate our molar mass. Okay, and so the molar mass is going to be 310.18 grams per mole. We can then go ahead and calculate our concentration, which would be mass over molar mass volume. Plugging our numbers in, 1.3 times 10 to the negative 4 grams all over 310.18 grams per mole. And then multiplying it by the volume, 3.95 liters. Double bracket that like that. So we're gonna get a pretty small number here. I have 1 point, with rounding, I'm going to round here, 1.06 times 10 to the negative 7. So we're going to call it 1.1 times 10 to the negative 7 moles per liter. Then, of course, we would have to multiply that number by 3 for calcium, and we'd have to multiply that number by 2 for phosphate if we want to figure out their concentrations. So this would just work out to 3.3 times 10 to the negative 7 moles per liter if I'm basing it off of this value. And this would be 2.2 times 10 to the negative 7 moles per liter if I'm using this value as well. And that's all she wrote. I hope you have enjoyed this lesson of You Got Hope Chemistry. See you next time.